back to where we were. Okay. Let's go back to sharing the screen. Well, we got some rain here. It's talking about chemical reactions. So today's lecture is about chemical reactions. And obviously, chemical reactions are about what happens when you bring elements together or break elements apart. Or not break them apart, but so you have a compound. Remember, multiple atoms that join together through covalent bonds are compounds. And so might be, or it could be very small things like metal type compounds, and you break them apart, you have a chemical reaction and you end up with new products. Or if you bring two products together and you join them together, you have a new compound. All of that requires energy. Often the energy can be rather a lot of substance. Might be fire, for instance, would be an example of the energy needed to break something apart. And we do that all the time with combustible engines and breaking, you use oxygen, for instance, when you're trying to break down substances. Now, in our body, we do this with the help of enzymes. So enzymes are important for speeding up a chemical reaction and are often needed. A lot of chemical reactions could happen if given enough time. A little small changes can happen where these elements would come apart and come together. But enzymes dramatically increase it when we're talking about biochemistry, or organic chemistry. But again, energy is often needed for these chemical reactions. And so again, chemical reactions involve chemical changes in matter resulting in new substances. The reactions involve a rearrangement and exchange of atoms to produce new molecules or new compounds. So you're going to see that we're going to have maybe something like methane get burned, and we're going to have carbon dioxide as the byproduct, for instance. Now, remember, elements, generally speaking, are not transmuted during any of these, or are not transmuted during these reactions, these chemical reactions. So we're not actually breaking the carbon atom into something new. We're just combining it with oxygen, for instance, or hydrogen, or oxygen is combined with hydrogen to make water. Those are examples of chemical reactions, but we're not breaking the oxygen, we're not breaking the hydrogen, the elements themselves aren't changing during these type of chemical reactions. And again, that would deal mostly with the electrons or the outer shell. So the nucleus and the neutrons all will stay intact. And for the most part, all we're talking about is forming new chemical bonds or breaking those chemical bonds in these chemical reactions. You don't break up an atom unless we're talking about nuclear bombs and breaking and fission reactions and stuff like that. So what is kind of the visual evidence of chemical reactions? A lot of it was, before, a lot of it was originally determined through just our senses. When a chemical reaction takes place, you can see a change. Like if you bring two chemicals together, you can see color changes. You can see precipitate, on your test tubes. You can see gas and bubbles and flames and heats or cooling taking place or light energy being given. So these are all examples of evidence, visual evidence of chemical reactions that have taken place. You may smell new smells. You join two chemicals together and all of a sudden you'll have an odor going around because of the new chemical that has formed. So those are all examples of chemical reactions that take place. So again, if you're doing some test tubes and you're working and you put substances together, maybe two clear substances, and all of a sudden you see a color in your test tube, or you see new solids forming and falling at the bottom of your test tube, or bubbles forming. Those are all examples of clues cues, clues that you can observe. And a big part of it is usually some type of heat is produced or heat is absorbed. So it either gets hotter or colder. Now, remember, we always, as chemists, we always like to look at using shorthand to help describe our reactions. So this is a way for us to, kind of like when you put words to describe an animal, that this is a dog. We all know what that means. So this is what chemists do. They use this shorthand to help describe what's happening in a reaction. So it provides information about the reaction. So we have formulas for reactants and products that tell what's happening, and the state of the reactants and products, meaning is it a gas, is it a solid, is it a liquid? Those are what I mean by states, right? So we know that states mean a substance can be in those different forms. And again, the formulas let you know how many atoms and things like that. The relative number of reactants and product molecules are required to do these chemical equations. So it's a lot like math. You have to, you don't just lose it. You just move when you do join two different numbers together, you're going to have a new a new number. Well, that's kind of like what we're doing with chemistry. So you would weigh out the reactants. Again, the reactants are the substances that are changing. So they are the ones, it's the before state. The reactants are the before state that are being used. And the products are what happens afterwards. What is the new stuff being made? Now, remember, this is a point that's been determined by chemical research that at one time people in the early days would not have realized. There is a conservation of mass. If you burn this bottle, the weight of this bottle still exists. It's just now a gas. So if you're able to gather all the CO2 or whatever gas that comes off of this combustion, because obviously oxygen is going to be involved. If you were to collect it in a balloon, it would weigh the same as this. You didn't lose this. It didn't disappear. And that's what we mean by conservation of mass. The mass still exists. So the idea is, at least in the universe that we live in, there's always discussions about multi-universes, and before the universe existed where things were a lot different. But in the universe that we exist now, matter cannot be created or destroyed. So in other words, even if you destroy this as far as the visual use of this bottle, the matter itself that made up this bottle still exists. It just exists in a different form. So in a chemical reaction, all the atoms present at the beginning are still present at the end. So we have not lost the carbon atoms that are in this bottle. Therefore, the total mass cannot change. Therefore, the total mass of the reactants will be the same as the total mass of the product. So what we put into the chemical reaction, that the weight of those products will still exist after the chemical reaction as products. So here's an example of the combustion of methane. So we're burning methane. Methane's a gas. And so whenever you burn something, you're using oxygen. So burning something in space isn't really happening. It requires oxygen to do so. So methane gas burns to produce carbon dioxide and liquid water. Whenever something burns, it combines with oxygen in the number of grams. So again, the oxygen is would also be reactants that are in the atmosphere. Methane's in the reactions. So maybe if I had a bottle of methane under combustion and I lit it, and obviously it would combine with the oxygen to form carbon dioxide, water. And so let's look at the chemical reaction. So over here we see our methane. I don't know if I can bring in, so over here you can see methane. Here's the carbon atom. Here's our 4 oxygen atoms. Remember, this is the chemical structure. So this is our outer orbital shell. Remember, carbon would be able to hold 4 bonds, 4 electron bonds. So it's holding 4 covalent bonds with these methanes. And if you remember from, it's been a while now, but oxygen can hold 1 or 2 bonds. And so now we have oxygen molecules. So this is what oxygen looks like in the atmosphere. It's always going to have not always, but mostly it's going to have 2 oxygens joined together. So this is what we typically see in the air. We'll see 2 oxygens joined together. And so this is, again, the chemical formula. And then here's how we wrote it. So we have 1 carbon plus 4 hydrogens plus 2 oxygens. Then the chemical reaction takes place, and that's what is signified by this big arrow. So it's kind of like an equal sign when you think about math. So the products become carbon dioxide, carbon with 2 oxygens, plus water. And so remember, we had to take into account the fact that we had 4 hydrogens, 1 carbon. So here's the 1 carbon combining with 2 oxygens. Now remember, in the atmosphere, there's going to be other oxygens, but basically what's going to happen then is there's going to be 2 of these hydrogens hooking up with 1 oxygen to form water, and then these other 2 hydrogens are going to form with another oxygen to form water, so that ultimately you have 2 waters. So again, you had to take into account everything. Now you might be wondering, what is these letters behind here? Was those grams, or what is that? Well, what this is signifying that is that that oxygen is a gas. So that's the state it's in. So here we have methane as a gas, oxygen as a gas, carbon dioxide as a gas, and then we have H2O. So what is this line? Well, this line is actually an L, representing that water is a liquid, as you know. So from this reaction, we would need to have at least 4 of these water molecules, because you have to take into account the other 2 hydrogens. And those 2 hydrogens combined by themselves, of course. And so that's what it says. The combustion of methane is balanced. So to show the reaction obeys the laws of conservation of mass, it must be balanced. So before, we didn't really see a balance. I was alluding to it, how it would be balanced by having 2 water molecules. In this slide, you see how it's balanced. Before, it doesn't tell you that it needs 2 of these oxygen molecules. So these are the players, but it's not balanced in this picture. And that's what the X is showing you here in this reaction arrow. So in this next slide, we see how we balance this chemical reaction. So combustion of methane is balanced. To show the reaction obeys the laws of conservation of mass, it must be balanced. And so again, this slide is showing how it's balanced. So again, going back to this chemical reaction, here we have our methane. That methane combines with 2 molecules of oxygen. Now remember, that means that the 2 oxygens are joined together, making ultimately 4 oxygen atoms. So you have 1 carbon atom, 4 hydrogen atoms for the methane. Remember, they're covalently bound. And then you have the 2 oxygen atoms covalently bound. Then you have a chemical reaction, fire. We burn the methane. That forms carbon dioxide. So this carbon is accounted for with these 2 oxygens. And then these 4 methanes, again, are going to join up with to form 2 water molecules. And so that's what you're seeing in this chemical reaction up here, and how everything's accounted for. Now we have 2 water molecules. Again, it's a liquid. That's why you see this line here. Carbon dioxide. And so we have our methane gas, our oxygen. We have our fire to burn it. Our chemical reaction takes place. You see the fire. So you got the visual cue. and the byproducts is the carbon dioxide and the water. So methane actually burns pretty clean if you think about it from the perspective of the atmosphere. Obviously, building up too much carbon dioxide in the atmosphere can have issues with global warming, but it's still better than breathing carbon monoxide, which would happen during some types of combustion, as you know, through combustion engines. But now, so again, the important point of this is, remember, we didn't gain or lose matter. And so that means when we have a chemical reaction, we have to take into account all the chemicals and chemistry that's involved. So going back to this slide here, you can see that's why the X was through here, because not all the atoms were accounted for. So we were missing how these were all joined. So when you see this slide here, you see the proper balanced explanation of chemical reaction taking place. So writing equations use proper formulas for each reactant and product. You're not a very good chemist if you don't put in the proper, you don't make a slide that looks like this that shows what really happened. You have to obey the laws of conservation of mass. Otherwise, you don't really have a well-written chemical reaction. So you haven't really accounted for it. So it'd be like writing a paragraph and not having your sentence, you're missing words in it. It would lose its meaning. So that's why it's important to have your chemical reactions written and equations balanced properly. All elements on reaction side also are on the product side, as I showed you. So everything that started on the reaction side takes place on the product side. Equal number of atoms of each element are on the reactant side is on the product side. So a balanced equation shows the relationship between the relative number of molecules of reactants and products that can be used to determine the mass relationship. So you can, again, if it's mass, you can weigh it. So again, that is the point, is when you look at chemical reactions, you have to make sure that the equation is balanced, just like any kind of math equation that you would do. You would need to make sure that you took into account all the numbers involved. I already alluded to this with you all when I mentioned, what does the G mean? What does the L mean? Well, now you have S as well. So we typically, in these chemical formulas, indicate the state that it's in. What is the chemical state? Is it a gas? So G would equal gas. L would equal liquid. And you can see it's italicized. And S would equal solid. If the chemical is dissolved in water, we have an AQ representing aqueous, meaning that the substance dissolved into the water as part of its chemical reaction. So here's some examples of recognizing reactants and products. So when magnesium metal burns in the air, it produces a white powdery compound called magnesium oxide. Burning in air means reacting with oxygen. Metals in general are solids, except for, of course, mercury, which is a liquid. So you're going to always have and down here, if you look at the reaction, you can see that magnesium has an S with it because it's a solid. So you're going to write the equations and identify the state of each chemical. Well, we know that magnesium is a solid, and then oxygen is a gas, and then the chemical reaction will result in magnesium oxide, a solid. And so that's how the chemical reaction is written. You're going to identify the diatomic elements, identify polyatomic ions, and determine the formulas. Anyway, so this is showing you how magnesium oxide is formed. Now you notice there's something missing. We had two oxygens over here. So you would need to account for that. So there would at least be 2 magnesium oxides formed. So these are examples of what you would do. Balancing by inspection. So this is when you look at the different atoms and you count for it. So it's kind of like what I did before. You're counting the number of atoms and seeing if you're missing something. We're missing something here, right? We're missing an oxygen. What happened to the other oxygen? So this is you taking the time to account for the reactants and whether or not the products match what went into the chemical reaction. So a polyatomic ions may be counted as one element if it does not change in the reaction. So here we have aluminum, iron sulfate, and we have our chemical reaction take place, and it ends up forming aluminum sulfoxide, I believe is what it's called, and a free iron. So what is shown in this reaction is that it took, that we're missing some stuff, right? So if an element appears in more than one compound on the same site, account each separately and add. So that's kind of what we're trying to mention here. Let me take a moment to give you an example from YouTube. Okay, now we're going to take a mental break and watch this 10-minute clip, and then I'll get back with you on my part of the lecture. Hang on a second.
Let's talk a little bit. Everybody without know it. So what are chemical reactions? Let's talk a little bit about chemical reactions. And chemical reactions are a very big deal. Without chemical reactions, you or I would not exist. In your body right now, there are countless chemical reactions going on every second. Without chemical reactions, we would have no life. We would not even have the universe as we know it. So what are chemical reactions? Well, they're any time that you have bonds being formed or broken between atoms or molecules. So what are we talking about there? Well, this is maybe one of the most fundamental chemical reactions. Once again, if this one never occurred, we'd be in trouble. We would not have any water. But let's think about what it is actually describing. So over here on the left-hand side, we have the reactants. Let me write that down. So here we have the reactants. These are the molecules that are going to react. And then we have an arrow that moves us to the product. So let me do that in a different color. So we have an arrow that moves us to the product, or we could say the products. And so what are the reactants here? Well, we have molecular hydrogen and we have molecular oxygen. Now, why did I say molecular hydrogen? Because molecular hydrogen, which is the state that you would typically find hydrogen in if you just have it by itself, is actually made up of 2 hydrogen atoms. You see it right over here. 1, 2 hydrogen atoms. And what we have, in order to have this reaction, you don't just need 1 molecular hydrogen and one molecule of hydrogen, 1 molecule of oxygen. For this reaction to happen, you actually have 2 molecules of molecular hydrogen. So this is actually made up of 4 hydrogen atoms. So let me make this clear. So this right over here, this is 2 molecules of molecular hydrogen, and that's why we have the 2 right out front of the H sub 2. This little subscript 2 tells us there's 2 of the hydrogen atoms in this molecule, and then this big white 2 that we have right over here, that tells us that we're dealing with 2 of those molecules for this reaction to happen, that we need 2 of these molecules for every molecule of molecular oxygen. And molecular oxygen, once again, this is composed of 2 oxygen atoms. 1, 2. So under the right conditions, so you need a little bit of energy to make this happen. If under the right conditions, these two things are going to react, and actually it's very, very reactive, molecular hydrogen, molecular oxygen, so much so that it's actually used for rocket fuel, you are going to produce 2 molecules of water. We see that right over here. And look, I did not create or destroy any atoms. I had one oxygen atom here. It was part of the oxygen molecule right here. And then I have the second one right over here now. Now they are part of separate molecules. I had 1, 2, 3, 4 hydrogens. I now have 1, 2, 3, 4 hydrogens, just like that. And actually this produces so we could say some energy, and I'm being inexact right over here, some energy, and then we could say a lot of energy, a lot of energy. So this is a reaction.
So you can see here that everything's being accounted for. For this chemical reaction to make this water, you needed to have 2 hydrogens, but 2 hydrogens and 2 oxygens wouldn't have counted for everything, because you wouldn't have a balanced equation. So if I was just looking at the H2 by itself. So that's why it's important to put the 2 in front of the H2 so that you have a balanced chemical reaction and the products are accounted for. Because remember, following the conservation of matter, you don't synthesize more hydrogen from de novo. You have to take it from the atmosphere or from the test tube or whatever the case may be. And again, it takes a lot of energy to break apart water. So you could break this apart, this water molecule, back into hydrogen and oxygen. What you would do is you would do it with electricity. You could have water and you put in 2 electrodes and you would end up seeing bubbles forming. You could actually capture the hydrogen coming off of it. So you could set up your water, put some electric metal in it from a battery or whatever. You'd have some little test tubes and you could collect the bubble gas that would come off of it. And what you would find is you would have hydrogen and oxygen, and you could actually light it and see a flame form. And then you would actually see precipitation again so you can burn it, making water again. So again, but it takes energy to do all of that.
Action that you just give it a little bit of a kickstart and it really wants to happen. A lot of energy. So one thing that you might wonder, and this is something that I first wondered when I learned about reactions, well, how does this happen? Is this a very organized thing? Do these molecules somehow know to react with each other? And the answer is no. Chemistry is an incredibly messy thing. You have these things bouncing around. They have energy. They're bouncing around all over the place. And actually, when you provide energy, they're going to bounce around even more rigorously enough so that they collide in the right way, so that they break their old bonds and then they form these new bonds. So whenever you see these reactions in biology or chemistry class, keep that in mind. It looks all neat and organized, but in a real system, these are all of these things just bouncing around in all different crazy ways. And that's why energy is an important thing here, because the more energy you apply to the system, the more that they're going to bounce around, the more that they're going to interact with each other. The more reactants you put in, the more chance that they're going to bounce around and be able to react with each other. Now, I'm going to introduce another word that you're going to see in chemistry a lot. This water, we have 2 water molecules here. We could call them molecules, but since they are actually made up of 2 or more different elements, we could also call this a compound. So water is, you could call it a molecule, or you could call it a compound. So this is a molecule or compound, while this molecular hydrogen, you would not call this a compound. And this molecular oxygen, of course, it's a molecule, but you would not call it a compound either. And just to get an appreciation of how much energy this produces, let me show you this picture right over here. That's the space shuttle. And this big tank right over here, let me this big tank, contains a bunch of liquid oxygen and hydrogen. And to create this incredible amount of energy, it actually just you mix the two together with a little bit of energy, and then you produce a ton of energy that makes the rocket, that makes the space shuttle. Well, the space shuttle's been discontinued now, but
You can see how cool chemistry really is. This understanding these basic
back when they
principles
did it to make it.
makes it possible for scientists and engineers to produce something like this space shuttle. And I was lucky enough to, of course, be alive when space shuttles was a big deal. And then my parents were lucky enough to be alive during people landing on the moon. And there's still great things going on with NASA and space stuff. We're having people, we have a helicopter like thing that's on Mars right now. And the sad thing about our news is we do not hardly talk about that. We talk about nonsense constantly in the news. And yet all sorts of amazing things are happening from scientists and engineers every day. But that's not big news. It's always some kind of nonsense. I mean, I'm not saying that those things aren't news, but let's put more interest in. Okay, I'm going on a soapbox, but there's so many amazing things, and people could be doing some amazing things. Like, when I was a kid, we dreamed of being, I'd love to have a life where we have Star Trek. But the only way that exists is by people becoming scientists and engineers, and for society to embrace it versus the typical pop culture. But here we are showing how a chemical reaction does something fantastic, amazing, getting a space shuttle so people can go out to space. And yet we on Earth hardly even pay attention to all sorts of amazing things that scientists and engineers are doing. They should be pop stars.
To make it get its necessary velocity. Now let's talk about the idea. So this reaction strongly goes in the direction of going to water, but it can actually go the other way. But it's very, very hard for it to go the other way. So in general, we would consider this to be an irreversible reaction, even though it is, irreversible sounds like, hey, you can't go the other way. It just really means that it's very unlikely to go the other way. You have to supply a lot of energy to go the other way. To make this reaction go the other way, you would have to do something called electrolysis. You're providing energy, et cetera, et cetera. But in general, the way that
Remember, electrolysis is what I was describing when you put the electrodes into the water and then you break the bonds. So I've seen that done with electricity. You just put the electrodes into the water, and that's the electrolysis he's talking about. But again, it does take an energy source, like hooking up a battery to the electrode.
this is written, because the arrow is only pointing in one direction, this is implying that it is irreversible. 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 Which probably makes you think, well, what about.
But we know it's not irreversible fully, just unlikely, as he mentioned. So normally you'd have the arrow go in the opposite direction if the chemical reaction flows back and forth naturally. But if it tends to be going in one direction, then of course we have the arrow going in that one direction. But again, as he just stated, it isn't really irreversible. It just takes a lot of extra energy to do so.
Reversible reactions? And I have an example of a reversible reaction right over here. I have one bicarbonate ion.
This one's actually very interesting because this one actually is what is found in your body and in your blood. Now, remember, when you break down nutrients, and of course, your nutrients are going to include carbohydrates, fats, and proteins, nucleic acids. These are all things you've eaten. We talked about this in our biochemistry subunit, if you remember. Well, when you break down fats, remember they're made up of carbon atoms, lots of carbon atoms, or carbohydrates, they're made up of lots of carbon atoms. You end up breathing out carbon dioxide. Ultimately, when you lose weight, you can lose water weight, but a lot of when you talk about really losing weight, like I need to lose 10 pounds, as an example. When you really have lost 10 pounds, most of that is actually from what you breathed out as carbon dioxide and the breakdown of the fat molecules for energy in your body. So carbon dioxide travels around in your blood as a biocarbonate. There's actually, you might not talk about it here, but the enzyme that's actually used is carbonic anhydrase. And what happens is when you when your body is breaking down fat, so you got your cell and you're breaking down the fats or the carbohydrates into smaller molecules that are ultimately carbon dioxide that you breathe out, it's traveling around in your blood as a biocarbonate. Um, and but he's not going to probably get into all that. But anyway, he's showing you how that chemical reaction at least takes place in part in your body as well.
And the word ion, that's just to use to describe any molecule or atom that has an imbalance of electrons or protons that cause it to have a net charge. So this makes this an ion, and actually, right.
So remember, this means there's an extra electron associated with this molecule, giving it a slightly negative charge. This one is missing an electron, giving it making it basically a proton, by itself, which actually would normally make an acid. If you remember, hydrogen ions are acids.
Right over here, this is a hydrogen. This is a hydrogen ion right over here. Both of these are charged. One has a positive charge, one has a negative charge.
Again, remember, it's going to be positive because of the proton.
But they are both ions. And this reaction right over here, you have the bicarbonate ion that looks something like this. This is just my hand drawing of it. Reacting with a hydrogen ion. It's really a hydrogen atom that has lost its electron. So some people would even say this is a proton right over here. This is an equilibrium reaction where it can form carbonic acid. And notice all that's happening is this hydrogen is attaching to one of the oxygens over here. And this is an equilibrium because if in an actual solution, it's going back and forth.
So you see how this became carbonic acid? And that's, again, remember, when you see those hydrogen ions, that's when you start to see that acid. But the point is the hydrogen joins and disassociates easily in solution. And so that's what the arrows are showing, going back and forth. So this is a product. So these are the reactants, this is the product, and then this is essentially kind of becomes the reactant, and these are the products when it goes in the opposite direction.
If you actually provide more reactants, you're going to go more in that direction. If you provide more of the products over here, then you're going to go in that direction. And so in an actual in an actual environment, in an actual system, it's constantly going back and forth between these two things, and different reversible reactions might tend to one side or the other. If you provide more of the stuff on one side, it might go in more in the other direction because they're going to be more likely to interact. Or if you provide more of this, it might go in the other direction because these might more likely react with their surroundings or disassociate in some way. Now, just to get a sense of, it's nice to kind of, are these just some random letters that I wrote here? Carbonic acid is actually an incredibly important molecule, or we could call it a compound because it's made up of two or more elements in living systems, and in fact, even in the environment, and even when you go out to get some fast food. When you have carbonated drinks, it has carbonic acid in it that disassociates into carbon dioxide, and that carbon dioxide is what you see bubbling up. Carbonic acid is incredibly important in how your body deals with excess carbon dioxide in its bloodstream. Carbonic acid.
So actually, as you remember, so now he's kind of getting into what I just described to you. So when this bicarbonate carbonic acid comes up to your lungs, again, there'll be an enzyme that will convert this to carbon dioxide that you'll actually breathe out.
It is involved in the oceans taking up carbon dioxide from the atmosphere. So when you're studying chemistry, especially in the context of biology, these aren't just, interesting things that seem very academic. These are affecting your real life and your body and your environment.
Does anybody have any questions at this point? I want to take one more look at this. Let's see if I can add magnesium.
Let me give you a few situations, and you need to tell me if the change that has occurred is physical or chemical. A paper is torn, a paper is burnt, water is converted to ice, we respire.
So remember, this kind of goes back to the idea of visual cues. Did you see did it get hotter? Did it get colder? Or did we see or did we see a flame? So which one of these would be the chemical reaction? I think it's pretty obvious.
Which among these are physical changes and which ones are chemical changes? To differentiate, we first need to know what physical and chemical changes mean. A physical change is a process in which the substance experiences change in its physical properties like shape, size, appearance, or state. There's no change in the internal structure or molecular composition. A chemical change, on the other hand, results in the formation of new substances entirely. The atoms of one or more substances are rearranged or combined to form a new substance. Now let's get back to our examples. First, a paper is torn. Is it a physical change or a chemical change? Are we getting a new substance entirely? Are the chemical properties changing? Not at all. The paper is just torn into two pieces. Paper is still paper and nothing else. Hence, it's a physical change. What about paper being burnt? Here, paper is converted to ash and smoke. New substances entirely. Hence, this is a chemical change. What about water being converted to ice? Here, only the state of the matter is changing, which is a physical property. Ice can be converted back to water too with a little bit of heating. Hence, it's a physical change. The last one is interesting. What happens when we respire? We utilize the oxygen we inhale, and after the respiration process, carbon dioxide is exhaled. Clearly, a new substance is formed. It's a chemical change. Whenever a chemical change occurs, we say there's a chemical reaction. And this is what we will study in detail. What do we actually mean by it? How do we know that a reaction has taken place? All this and much more in the coming lessons.
Let's see. Everybody still awake? Okay. Anyway, does anybody have any more questions? We're going to probably just watch one more video together. And then I would like for you to turn in your notes and so forth. So we're going to watch one more together.